Hello guys, how's it going? Can you hear me? No, we have this room. Yeah. How's everything? Is everything fine? Can you hear me? Well, let me check if sound is okay. Okay, the sound must be increased. Okay, now it should be good. Nice, great. Grace. Yeah, you're welcome. Thank you very much for joining today's stream as well. Well, without you, these streams do not mean anything. So thank you a lot for joining again. Today we're gonna talk about graph algorithms. This is our first topic stream on graph algorithms. Initially, we will start from the basics at the beginning. So we're gonna cover from the beginning, all over from the beginning, and we are gonna go forward. So even in today's live stream, at the end of the live stream, we're gonna also solve a bit more complex problems, but especially in the future live streams, in the next sessions that we're gonna... Can't hear me? Can you hear me now? Can somebody else please confirm if you can hear me? Okay, you can. Nice. So, yes, but in the next topic streams of graph, we're gonna go over on more complex problems as well. Around the first hour of this live stream, each live stream is for 2 hours. In the first hour, in the first half, we're gonna more cover the basics, but we gradually will move on to more advanced problems. Okay, shall we start? Well, initially at the beginning, we're gonna talk about what a graph is and why do we even use them, and what are the types of the graph, etc. So we're gonna start from this point, which is the very beginning of our discussions on graphs, but then we will gradually move on to more advanced things. And you do not need to know anything already to understand everything that we're gonna cover in this session. I mean, that was my goal. I mean, even if your rating is 0, you can join these live streams and learn everything all over from the beginning, and we're gonna move forward together. So we're gonna start from, you need no knowledge at the beginning, and we're gonna start talking from the very beginning of it, and we're gonna very fast get to solving complex problems. Okay, are you ready to start? If you're ready to start, please use this emoji. Oh, where are the emojis? Sorry, this emoji. Nice. So seems like everybody are ready for it. Nice. Nice. Okay, I hope it helps, and whenever, if you felt like you like this stream, I mean, we haven't started yet, but in the when we started the live stream, if you felt that you liked the video, you can support my work by liking the video or subscribing to the channel. You do not need to do that, but I think if you do, that would definitely help this work. So let's start talking about the graphs. I mean, initially we wanna talk about what a graph even is. Okay, this is the first thing. When we want to talk about the graphs, The first question that we want to answer, we need to answer is to what is a graph? Well, in simple words, a graph is a set of some vertices or some points, we can say, some vertices. Vertices are like points and some edges. Some edges. And edges are, in simple words, lines. So we have several points on the plane. We have several points that we call them vertices. And there are several lines between them. The lines connect, each line connects two of these points. So each of these edges connects two of these vertices. So we have a set of vertices. We always call them vertices, but in fact they are just some points, and they are connected by edges. Some of them are connected by edges or lines. So for instance, this is a graph, for example. We have some vertices and some edges connecting them. For example, we have these 5 vertices in here, and we have 6 edges that are connecting some of them. So what is this? I mean, okay, so we know that a graph is this. It is a set of vertices and a set of edges. But why? I mean, what's the point of it? Well, the point is that graph is extremely helpful because the job that it's doing for us is modeling. I mean, it's an abstract concept that we can use we can consider several things and we can model them to graphs. For example, what can be modeled to graphs? Can you help in here? I mean, can you suggest some real world examples that can be modeled to graphs? I mean, what do we mean exactly by this modeling? We say that the usage of graphs is modeling. But can you give us some suggestion? Roads and cities or places, Google Map, region, roads. Yes, nice, exactly. For example, one of them, or friendships, nice. Yes, you will see that we have different examples. They can all be modeled with graphs. For instance, let's go over the examples that you mentioned. For instance, we can have several cities or several junctions, whatever. So for example, we can map it like this. It's like we have several cities. So vertices can model cities. This is one example. But this is one thing that we can model. So vertices can show the cities, and edges can show the roads between them. For example, okay, we have this city number 1, city number 2. They are different cities. For example, let's use some real world names. For example, this is New York. This is, for example, London, Tokyo, Paris, or something like this. And then we consider the roads between them. I mean, even the roads, or for example, even if we use not only, we can use, for example, buses, we can use cars, we can use airplanes. So we can just save that if I want to go from New York to this city to London, for example, what is their distance? I can even write their distance on them. that we will get into. Sometimes on edges, we also write a number on them. Or they can all be cities of the same country. So they can be all the cities of the same country. This is the map of a country. And we have them in here. For example, we have all the cities in here. And we know that there is a road between these two. For example, they are all in the same country and we will consider the roads. For example, there is a road between this city and this city. There is a road from this city to this city. There is a road from this city to this city. So for instance, if I want to start from this city and go to this city, first I need to use this road to come here and then use this road to come here. And then I can apply several graph algorithms, for example, to find the shortest path from this city to this city. And as I said, I can also write the length of these passes. For example, this path is 13 kilometers. This one is 20 kilometers. This one is 8 kilometers, and so on. And this say, for example, if I want to start from here and go here, my path is going to be 33 kilometers. Because first 13 kilometers to get to here, and then 20 kilometers to get to here. So this is one thing that we can model to graphs. This is one usage that graphs can have. Another example that you mentioned, that was also a great example. It is friendship. For example, consider Facebook. Let's take an example of Facebook, for example. Assume that vertices are the users. So assume that vertices are our users. These are all the users that we have. We just show each one of them with a point. This is user number 1, user number 2, user number 3, and so on. There are many users. There are millions or billions of users in Facebook, and for each one of them we put a vertex. And between two we draw an edge if and only if they are friends with each other. Then we're gonna have a graph like this, for example. We're gonna have a graph like this. And again in here we have an abstract model that we can keep that which people are friends with each other and which are not. So again, it's like we can model everything to graphs. And then using this graph, we can solve so many complex problems. For example, if we want to find out that for each person, if we want to find out if two people, how many mutual friends they have, it's only enough to find out that in this graph how many vertices exist, that both this vertex has an edge 2 and this vertex has an edge 2. So it's like we want a path of length 2 from this vertex to this vertex, and we want to consider that, find out that which vertices can be the middle vertex of this path. So this is another example. Now consider that we have, for example, Instagram. This time we don't have friendships. Instead we have followers. So this time what we can do is that we have users in here, but we cannot only draw edges because one person follows the other one. And maybe the other person has not followed this person. This is not a two-way relationship. It's possible that X follows Y and also Y follows X, but it is not necessary. It is possible that only one of them follows the other one. So you see that in here, other than the edges, we need to consider a direction for each edge as well. So we can draw a graph like this. For example, this person follows this person, this person follows this person, and this person follows this person. Again, for example, assume that this person is like a celebrity. A lot of people follow him or her. And we're gonna have a graph like this. So you see that sometimes, we have this abstract model of graphs, and you see that sometimes we also write a number on graphs, as we saw in here. that, for example, shows the length of that path. But we do not always need that. The abstract model is that graph that we have, but there are some extensions that we can have as well. For example, sometimes we might also need to write numbers on the edges. Sometimes we also draw a direction for each edge, sometimes, and sometimes not, and sometimes both. Sorry for that. This issue tends to happen a lot, unfortunately. Sometimes we also draw a direction for each edge, right? So we can have all this, and sometimes both. Sometimes the roads are, for example, again, we have this example of cities and roads between them, and we have our roads directed. For example, there is a one-way road and it also has some length. So not only we draw a direction, but also we write a number on it. For example, we write 15 on here. So we see that we can have different types of graphs. Some graphs can be very simple. We do not add anything else to them. Sometimes we also have directions. Sometimes we also have edges, etc. So this first gives us some intuition that we can have different types of graphs. Graphs can be analyzed in many ways and can be classified in many ways. But for instance, I'm gonna just mention several important and well-known types that graphs can have. One of the very well-known graphs that we have, first of all, let's just consider being directed or not being directed, and also being weighted and not being weighted. So we have two ways for this, and either it is directed or it is not directed, and two ways for this, even it is weighted or it is not weighted. So how many ways do we have by only considering these two factors? Are you from India? No, I'm not from India. I'm from Iran. Yes, exactly. Exactly. So we're gonna have two ways for this one, two ways for this one. So we have 2 by 2 equal to 4 ways in total. I mean, each of these two can come with each of these two. So we have 4 ways. How are those 4 ways? For example, we can have an undirected, unweighted graph. So it's this case and this case. This is the simple one that we had at the beginning. For example, in the database of Facebook, we can have the set of all the users and their friendships. It is undirected and unweighted. I mean, we don't put a number on their friendship. Either they are friends or they're not friends. There are just 2 ways. If they are friends, we draw an edge. If they're not, we do not draw an edge. So for example, an example of it, for example, can be Facebook example that we were considering. The second case can be directed, unweighted graph. So this time we consider this case and this case. So can give me some example of that? For example, among the examples that we mentioned today, which case is directed unweighted? City, Instagram. What do the rest of you think? Yes, exactly. Instagram and followers are exactly the second example, because again, we do not put a number on how much this person, for example, has followed the other one. There's no such thing. They either follow or do not follow. So Instagram is an example that, for example, this person has followed person X, has followed person Y. There's no number on them. They're just followed. In the Facebook example, they were just friends. So there was no need for even the directions. But in Instagram example, directions are needed. So, exactly. So there are two other types as well. Now, let's consider the weighted examples. Now, again, we have undirected. Weighted graph, and we have directed weighted graph. Now let's consider examples for these two cases. For undirected weighted graph, what are the examples? Which example was working in here for undirected weighted graph? And also for directed weighted graph? Exactly, roads and map. So in other words, yes, exactly. If we have two-way roads, if we have a map with two-way roads, for example, this map shows that how much time it takes to walk from a junction to another junction. It is two-way because if you can walk this way, you can walk the other way as well. So in this way, we can just for each two junctions, just save that if we want to walk from here to here, what is gonna be, how much does it take? For example, it takes 5 min. If it takes 5 min to go from X to Y, we just write 5 in here. Right? And what about directed weighted graph? It is very similar to the previous one with only one example, with only one difference. I mean, this example has only one difference. Exactly, one-way roads. One-way roads. Yeah, or even if you have only one-way flights, that would work as well. But yes, this time we have one-way roads. For example, this time we are really considering roads and cars. Maybe we have some roads that the cars can go from one side to the other side of the road, but it's only one way. You cannot use it another way. So not only you need to consider the direction, not only you need to consider the length of this road, but also you need to save that how much it takes to go from X to Y. For example, it is for example 10 kilometers. If it is 10 kilometers and it is from X to Y, it is one way. From X to Y, you write 10 and you will direct it from X to Y. And these are the 4 types of graphs. This is not, there are a lot of more things to talk about when we're talking about a graph, and there are many other ways to classify it as well. But for now, these 4 types are the main types that you need to know about the graphs. So for each graph, there are 2 characteristics that are really important, and each of them have 2 ways. Either it is weighted or unweighted, so this is one thing that you need to take care of, and also it is directed or undirected. These two characteristics are the first two characteristics that you need to know about a graph. This is very important. For example, if you know that you have a weighted undirected graph, it's gonna be this way. If you have a directed unweighted graph, it's gonna be this way. This way. So these are the four types you have. It is two characteristics, each of them have two ways, so in total it's gonna be 2 by 2 equal to 4 possible ways for them. Okay, so these are the types of the graphs that we're considering right now. And for example, when you open a CF problem, you most of the time see it. For example, it says that we have an undirected unweighted graph, or we have a directed weighted graph, etc. And there are many algorithms for each type of these, for each, let me say it like this, for each one of these types. And some algorithms work for all of them, for just more than one type. Some algorithms work for more than one type. But some will only work for only one type of them, for some characteristics, for some specific characteristics they work. For example, in directed graphs, there are several things, there are several concepts like DAGs that are only considered for directed graphs. Or there are some algorithms like DFS that finds the shortest paths. But it can only find the shortest paths if we are talking about unweighted graphs. But there are also some concepts like connectivity, and many other things. Each of them, for example, can work for some subset of these types that we were mentioning. So each one of these types have their own algorithms, but some algorithms work in not only one type of them, in a subset of these graphs, that we're going to go over them one by one. So in these topic streams that we're going to talk in this session and in the future sessions, we're going to go over all of these algorithms one by one, and we're going to actually solve problems from them. Okay, is everything clear so far? If it is, please again use this emoji or say that in the chats. Nice. Nice. So far so good. Okay, so now let's talk about another important thing, and this is the first question that we want to think about as well. So there is some other important concepts in graphs, that is connectivity in graphs. And let's say that for now, in here we are only considering undirected, unweighted graphs. Okay, and first we're going to talk about this, and then whenever needed we will extend it to other types as well. But for now I'm just talking about undirected, unweighted graphs, just this simple form of graphs that we have. Now we want to find out if a graph is connected or not. What do I mean by being connected? So we know that we have a set of vertices and there are some edges between them. There are some edges like this between them. Connectivity means that if a graph is connected, a graph is connected if starting from each vertex or each node. Vertices are also known as nodes. So if you hear nodes, know that that is the same thing as vertices. So because of that, I write node in here so that you hear this as well. If starting from each node, you can go to any other node using the edges. So what does it mean? It means that if I choose any of these nodes, for example this one, and I can go from this node to any other node just using the edges. For example, let's consider that from that red node, I want to go to edge. I can go from this node to this green node, and then using this edge from this green node, I can go to this blue node. So I see that from the first node, I can go to the second node. Now a graph is connected if this is true for every two nodes. So from any node, I can go to any other node that I want. Then we say that this graph is connected. So let's give you an example of when the graph is not connected. A graph is not connected, for example, in this way. For example, if our graph looks like this. This is, for example, our graph. This graph is not connected. This graph is not connected. Why? Because if I start from this node, there's no way that I can come to this node. You can see that this part is not connected to this part at all. So if I choose one node from this part, it can never go to one node to this part. So in this situation, we say that the graph is not connected. This is an example of a graph that is not connected. But when you see this graph, the first graph, you see that it is completely connected. For any two nodes, I can start from one and go to another one. And that's so simple for me. So this is the question that we want to find out. I mean, we have a graph, we want to find out if it is connected or if it is not. So before that, how can I do this? How can I give a graph to a computer and ask the computer if this graph is connected or not? How can it solve this problem? You know, I mean, we should write a code for it, right? We want to write a code that we give a graph to it and it tells us if it is connected or not. Well, first of all, we need to think about how to give a graph to a computer. I mean, the first question is how to give a graph to a computer. I mean, we should tell the computer that what our graph is. How can we do that? Should we, for example, take a picture from this graph and then upload it, and then the code will analyze it and tell us that if it is connected or not? We should find a way to for our code that it will be able to take the graph as its inputs and process something in it and give us some outputs, run some algorithm on it and give us some outputs. But the first question is that how to give the graph to a computer. And another question, how a computer can store a graph in memory. These are the first questions that come to our minds. So, okay, this is a graph and the computer wants to process something on it. But how can a computer first comprehend what our graph is? So do you have any idea for that? Let's take a look at your ideas. Create visited array, right? Input n and m, then write connected nodes. Great, awesome. Attention matrix or attention vectors. Okay. Yes, you have very good ideas. Very good ideas. And do not forget that, hi. And do not forget that for now our graph is just an unweighted, undirected graph. So yes, as you mentioned, one thing that we can do, so now the question is that how we can store our graph in computer. How can computer get a graph, an input, and process something in it? You had very nice ideas. We can just input, for example, if we want to tell computer about our graph. Well, first of all, we should tell it that what our graph is, and then it can run some algorithm in it. It should know that what our graph is. We want to tell computer about our graph. So as I said, one way that first came to mind was to take a picture from it and give it to the computer. But it is so complex how it should then process the picture and find out what this graph is. There are better ways to do that. And one way that you mentioned is to just first give the computer the number of vertices. So if you want to give the information of your graph to the computer, the simple way will be like this. First give it n, the number of vertices. Most of times we show the number of vertices with n, and sometimes the number of vertices, and sometimes people use v as this number, but usually we use n. So even sometimes they use v and e for the number of vertices and the number of edges, but usually n and m will be used. But if you saw v and e, you should be familiar with that as well. These are just some variables, so their name is not important. The important thing is that what value is inside these variables. And m is the number of edges. So when we want to give a graph to computer, first let's enumerate our vertices and edges. So let's give some identity to our vertices and edges. For example, if this is our users, for example, in Facebook, we have 5 users, for instance, and these are their friendships. These are their friendships, for instance. So what is n? N in here is 5. So we should first give computer the value of n, which is the number of edges that we have, the number of vertices that we have. And then how many edges do we have? We have, again, I think 6 edges we have. And now, after that, now the computer knows that. So let's see that what the computer knows so far. It knows that we have 5 vertices, which are, for example, this model is, for example, for our users in Facebook, for example. But the computer doesn't need to know to have any idea about that as well. The only thing that the computer cares about is what the graph is and what you want to do with it. Okay, so what computer knows is that you have a graph with 5 vertices, and we have 6 edges, but it doesn't know yet that how are those edges. I mean, between which vertices those edges are. So next, in 6 lines, we will introduce all the edges to the computer. So the first edge, for example, is between vertices. So after giving me the value of n and m, first we give this edge 1 and 5. We say that there is an edge, one of the edges is between 1 and 5. Then the computer knows that, okay, there is an edge between 1 and 5. Then we also give it the other edges. So right now I'm talking about how to tell the computer that's what our graph is, and then we need to talk about how the computer can store this data in memory, how to save this in a good way. So there's an edge between 1 and 5, there's an edge between 1 and 4, there's an edge, and the order does not matter, I can give it in any order. There's an edge between 2 and 3, then between 4 and 3. So the order doesn't matter, and because it is undirected, you can write 3 and 4 or 4 and 3, both works. And there's an edge between 1 and 3, or I can write 3 and 1, there's no difference. And 1 between 2 and 4. Let's write 2 or 4 and 2, no difference. So this way, the computer knows that, okay, there's an edge between 1 and 5, there's an edge between 1 and 4, there's an edge between 2 and 3, there's an edge between 4 and 3, or 3 and 4, no difference. There's an edge between 3 and 1 and 4 and 2. So this way, it completely knows that what our graph was. By just giving these numbers, we told the computer that, okay, this is our graph. There's no need to send an image or anything like that. This way, easily we know that what are the edges. And how we can store it? Well, there are different ways to store, but I don't want to go over some details that is not going to need it in here. So first of all, we're going to go over all the other things as well, because it is important for me to stick to the important things. I tell you that what is the efficient way that the computer can store these values, that whenever it wanted, so it has the data of the graph. So now that we get this input, we need to store them somewhere, and we need to have some organization, we need to have some structure on how we want to store these values. Well, for that, one thing that we can do is that for every vertex v, for every node v, let's keep, again, let me mention that again, node and vertex are the same thing in graphs, so you can use any of them. For every node v, let's keep all the nodes or vertices adjacent to it. And what does this adjacent mean? Well, adjacent means that they are neighbors. I mean, for each vertex, you want to find out by adjacent vertices. For some vertex x, we say that y is adjacent to x if and only if they have an edge between each other. So we say that for every x, we want to store that what are the vertices that are adjacent to this vertex. There are going to be some of these vertices that are going to be adjacent to vertex x. And how we can save this? How can we save for each x what are the vertices are adjacent to x? Yes, adjacency list is a good option. Can you say that what data structure in C++ we can use to store all these? Exactly, vectors can work well. Yes. So you can either use arrays or vectors. I can define n arrays. So one option is to define n arrays. So this way I have to have two-dimensional arrays, because I need to have n arrays of maximum size n, because maybe the number of adjacent vertices, for each vertex x is at most n minus 1. And in here we only consider that between two vertices there is only one edge. I mean, we cannot have two friendships between two people. There is either an edge or there is not. And no vertex has an edge to itself. So for now, we are just considering that between each two vertices, there's only one edge and there's no edge from a vertex to itself. This type of graph has a name that we get into it, but for now, let's not focus on it. So this is the structure of our graph. So one thing that we can have is to have a list of adjacent vertices. It is a two-dimensional array. I mean, its size is going to be max n by max n. So initially we can set all the values to -1. When it is -1, it means that there's no value there. I mean, there's no vertex there. And only for each one of them we will store in for x, if there are, it has only, for example, 4 adjacent vertices. What we can store in edge of x is an array of length n, right? So edge of x can look like this: y1, y2, y3, y4, and then the rest of them can be -1 because there's no other adjacent vertices anymore. So -1 is a sign that, okay, we're done. There are no other adjacent vertices. So -1 is just like a sign for no value. It's a sign for us that it says that, okay, we're done with all the vertices that are adjacent to it. But a better way is to use a data structure in C++ named vector. We can store the adjacent vertices of each vertex in a vector. What is the difference of a vector and an array? The point is that the size of a vector is dynamic. So the size of a vector is dynamic. So it's not a fixed length for a vector. We can change the size of a vector. In arrays, we saw that we need to set the size of the adjacency list of each vertex to be n initially, because maybe at most it takes n. So we needed to take the maximum possible space, the maximum space that can be possibly used, and even it uses only 4 of them, but we need to store n numbers because maybe they are needed. But in vector, we do not need to consider n numbers and only use, for example, 4 of them. The size is dynamic, so we can just, if we're gonna need 4 numbers, we can just have 4 numbers. We can just have an array of 4 numbers. So vectors are exactly like arrays. The only difference is that they're dynamic. So what we can do, how does this vector work? I mean, when you have some vector, I just want to give you some brief explanation of vector as well, so that if you're not familiar with it, you define some vector and you can push back some value to it. It stores it to the end of your vector. For example, you can say v.pushback, for example, 5, and then v.pushback 2, then v.pushback 3. Then this way, at the end of here, you're gonna have an array like this, an array of size 3 with 5, 3, and 2. So you're gonna have an array like this at the end. For example, if you see out v of 0, you will get 5. If you see out, let's use an end. If you see out v of 2, you're gonna have 2. So this is gonna be v of 0, v of 1, and v of 2. So this is how vector works. Their sizes are dynamic, and you can store different values in it. You can push back different values to the end of them. So if we use this, how can we store our graph? We can just initially, we know that we can have an int of n and m. The number of vertices and the number of edges will be stored in 2 variables, n and m. And then you have some vector ints of these adjacency lists. Their size is maximum value for n that we have. So this capital N is a constant value that we define. That is the maximum number of vertices that we can possibly have. So we need to tell the computer that this graph that I'm telling you, I mean, when you're writing a code, you should set some limits. I mean, if this code is gonna solve some problem, you should set some limit for it. That's at most how many vertices this graph can have. Because the memory and the capability of this computer is limited. So you need to say that, okay, if you're gonna solve this problem, I assure you that I never give you more than 10 to the power of 5 vertices or 10 to the power of 6 vertices. So I will at most give you 1 million vertex. So you need to tell the computer that I want you to solve this problem. I mean, you write some algorithm, do this, do that, but you should also set some limits for this. That, okay, at most, you will solve the problem for at most these many vertices. So this max n that we define here, that I show with capital N, is the maximum number of vertices that this code can work for at most. So let's assume that it is 1 million vertices. So I show it with 1,000 by 1,000. This way it is more clear if you write it 1,000 by 1,000. You can also write 1 and then 6 zeros, but that's a bit hard to read. That's why I use 1,000 by 1,000. And it is always good if you add some small number to it as well. There's something, because there's gonna be some issues if you not do that. So anyway, you consider it 10 to the power of 6. So let's add just some small number to it as well. Later on you understand it better, why it is good to add some small number to it as well. So I'm gonna solve this problem, the computer will solve this problem for at most 1 million vertices. This is the maximum that it can solve the problem for. Because it's not, we cannot do it without setting any limits. The computer has some limits, and we need to set that, okay, at most, okay, the graph that I will give you has at most these many vertices. This memory and everything that the computer has some capabilities, so we need to consider some limits for it. So we have at most 1 million vertices, and as I said, we also add a very small number so that we are sure that for everything from 1 to a million it works. If you don't add it, maybe for 1 million itself it doesn't work. Maybe there would be some +1, -1s at the end. So we add 20 so that we make sure that for everything from 1 to 1 million it will work. These are the things that we define initially. So we can store a graph in here as we defined with at most a million vertices and some edges. And in here, in our main, when we want to input the graph, we first scene n and m. So we get that what are the values of n and m. We store them into variables n and m, and then we have a for. As we said, we need to now take all the edges one by one. I equal to 0, I less than m, I plus plus. This is a for that has m steps. We need to scene the edges. So first we have int of u and int of v. We define u and v that we have an edge between them. Usually for vertices we use variables like u and v. So we have two vertices that there is an edge between them. We define two variables and then we scene them. We scene u and v. So for example, first initially we define n and m, and we scene n and m. In this example we get 5 and 6. Then m times we define some temporary variables like u and v, and we scene u and v. For example, first time u is 1, v is 5. Then u is 1, v is 4, and so on. I scene u and v, and then in here I'm going to use 1-based indexing, so I'm not going to say u minus minus v minus minus, if you know what I'm talking about. So because this is not something I want to focus on right now. So I have u and v, and I see in u and v, and then it's just enough to say that edge of u dot pushback v. So to the end of the list of adjacent vertices to u, I have to push back v, and to edge of v to the end of the list of all the vertices adjacent to v, I have to push back u. And this way I have all the vertices and edges. I know the number of vertices is n, the number of edges is m, and I enumerated all the vertices with numbers from 1 to n, and then I add these edges between them. And yes, I assumed that my graph is undirected and unweighted. Can you say that if the graph was directed, it wasn't undirected, it was directed? Can you say that I mean, can you say that what should change if it was directed instead of indirected? Yes, we're gonna do problems in this lesson. We get to problems as a lesson. Exactly. We only add edge from u to v. Only edge of u dot pushback v. Exactly. So if it was directed, exactly. If it was directed, not undirected, we should not add this line. We only say edge of u dot pushback v because there's only an edge from u to v, not from v to u. So this way we can store a graph in the computer. So we gave the graph to the computer and now it can be stored there. So now the question is that, okay, how now we can run algorithms in it? Everything is ready. The computer completely knows that what the graph is. So now it can do whatever it wants with it. Okay, so now we gave a computer to we gave a graph to the computer and we saved it there. Now it has all the data. Now it can do anything it wants with it. So the computer has our graph now. Now the computer can do whatever it wants with this graph. So now we need to define that, okay, do this or do that and give me some output, give me some answer. Okay, so this is where the algorithms come into place. This is where we have different algorithms that we can tell the computer, okay, do this, do that, right? So this part is the important part that we're gonna talk a lot. What are the things that we can do with graphs? We're gonna discuss them, and most of the problems are about this part. I mean, what you want to do with this graph. Okay, everything clear so far? If it is, please again use this emoji. And how to take weighted graph as inputs. We get into that, but you can, for example, also, other than, for example, v, you can also store another number that is the weight of that edge. For example, if there is an edge between u and v with weight 10, in adjacency list of u, you can store v and 10. You can store a pair of v and 10. It means that there's an edge to v and its weight is 10. But we get into that in detail. For now, we're talking about unweighted graphs. Nice, nice. If the graph has directed and undirected edges, what we do? Well, if you have both directed and undirected edges, you have to. That's nice, guys. Thanks. So, if you have, you know, an undirected edge is like a two-way edge. So it's like it is both this way and this way. So any two-way pass is like two one-way passes. So whenever you had an edge that was undirected between u and v, you can add both of these edges. Whenever it is one way, it was only from u and v, you will only use this edge. So you have an if statement. If it was one way, only add this edge. If it was two way, add both of these. In case there was both one way and two way edges, right? Nice. So now let's talk about what we want to do with this graph. So remember what was our question? The thing that we wanted to think about was that we wanted to see if a graph is connected. Okay, and then these questions arise. So now we have a graph. We want to see if it is connected or not. What we can do? Well, first of all, I can say, is it possible to have both in the same graph? Well, if you have both undirected and weighted, directed and undirected, well, it is not different with only having directed edges. I mean, having both directed and undirected is the same as having directed edges. I mean, they are equally powerful. But the point is that directed edges, the model that has directed edges, has more complexity, but it is more powerful. I mean, you're adding a new characteristic to each edge, so you're making it more complex, but it can cover more things. It is more powerful. So if you have both directed and both undirected and undirected edges, it's the same as having only directed edges, because each undirected edge between u and v can be also modeled with a directed edge from u to v and an directed edge from v to u. So if you model something to a graph that has both directed and undirected edges, you could also model it to a graph that only has directed edges. You know what I'm talking about? I mean, this model that uses only directed edges is equally powerful with a graph that has both directed and undirected edges. So usually we do not use this because this is the same as having directed edges. I mean, if it is possible to not have any direction, then that is simpler, so it's better. So we do not add any other characteristic for the direction of the edges. But if you need to, if at least for one vertex you need to store direction, then for all of them you can store direction. You see what I'm talking about? So usually we do not use this model because it's not helpful. If for some vertex, if for some edge you have direction, then you can keep direction for all of the edges. Then it is better. I mean, it's more structured if for all of the edges you have the directions. So such a graph usually is only a directed graph, and those two-way graphs, two-way edges can be kept like two one-way edges. Okay, you became grandmaster at what age? I think it was 3 years into doing competitive programming. I think I was 17. The first time I became grandmaster, I was 17. After 3 years of doing CP. And when I started, I was 14. I started Olympiads and I started CP. Okay, so let's get back to our question, how to check if a graph is connected. Well, the point is that we said that a graph is connected if for every two vertices, for every u and v, there is a path from u to v. There is a path, not only an edge, but it can be several edges that connects u to v. But in other words, I can say that as a fact, I can say that it is enough if I check this for only one vertex. For only one vertex, I check if it is connected with all the vertices or not. If it was, then the graph is connected, otherwise it's not. What do I mean? I mean that instead of checking for each u and v if they have a path to each other, only take one vertex. Let's name that, for example, vertex 1. For vertex 1, if there is a path from vertex 1 to any other vertex, then the graph is connected. Then there is a path from any vertex to any other vertex. I mean, if you see that vertex 1 has a path to all the other vertices, so in other words, vertex 1 is connected to all the vertices, then those vertices are also connected with each other as well. Because for every u and v, I mean, in the worst case scenario, from u you can go to 1, and then from 1 you can go to that other vertex v. So my point is that you do not really need to check it for every 2 vertices. You can only check for 1 vertex if all the vertices are reachable from this vertex. For instance, in here, in this graph that was not connected, any vertex that you choose, it just can get to a subset of vertices. No, you cannot find 1 vertex that it can get to any other vertex. But in this example, if you take any vertex, for example, this one, from this vertex you can get to any vertex. Therefore, the graph is connected. If it was disconnected, you could not go to all the vertices. So what I'm saying is that to check if a graph is connected, it's only enough if you start from it. If you start from 1 vertex of it, let's say, for example, vertex 1, an arbitrary vertex or vertex 1, and try to find out if all the vertices are reachable from that vertex. So our question will be this. Even if we want to find out if a graph is connected, our question is that if all the vertices are reachable from vertex 1. Is it clear so far? So I changed the problem. I simplified the problem a little bit, and now I say that it's only enough to find out if from vertex 1 all the vertices are reachable. If it is, please use this emoji or write that in the chat, and if it's not, tell me to explain it again. So the point is that it's not needed to find out for every 2 vertices. You can just, for 1 vertex, find out if all the vertices are reachable from that vertex. And now, how can I find that out? I have vertex 1, and I want to find out if from vertex 1 all the vertices are reachable. Well, what I can do is this. I can write a function, for example, that will traverse the graph. So basically, I want to start from vertex 1 and traverse the graph. I mean, just move on the graph and see if I can visit all the vertices. I want to start from vertex. Let's write the number 1. I want to start from the number 1, traverse the graph, and see if I can visit all the vertices. That's my question. So what I can do is while I'm traversing the graph, I can keep an array that for each vertex I can keep if I have visited it so far or not. So I can have a boolean of v's, and again its size must be max n, that we defined earlier, the maximum size that n might have. And this boolean, if viz of v is true, it means that okay, I visited this vertex. If viz of v was false, it means that I haven't visited this vertex so far. At the end, I want to make the visited of all the vertices true. I want to visit all the vertices. If it was possible, then the graph is connected. If I can start from vertex 1 and visit all the vertices, then it means that the graph is connected. Otherwise, the graph is not connected. So what I can do is this. I can write a function that does this traverse. So the question is that how can I move? How can I walk on my graph? How can I traverse my graph? I can write a function, for example, and I can have a void of traverse. This is nothing complicated. It means that, okay, assume that I'm on vertex v. Why do I use function? Because I might need to call myself with another input. For example, it means that, okay, in traverse, it means that I'm on vertex V right now. And maybe I will call this function with another input later on. Right now I'm traverse and I'm on vertex V and I want to visit all the other vertices as well. And then I can call it with another function. For example, okay, now I entered another vertex. So traverse of V means that I recently entered vertex V. And now I want to search the graph and try to visit new vertices. Okay, so each time I'm trying to visit new vertices. Okay, and in traverse, I can first of all, when I'm in vertex V, whenever guys something was not unclear for you, feel free to say that in the chats. Feel completely free to say everything that is not very understandable for you in the chats. So in my traverse function, I first of all say that vis of V equal to true. Okay, I visited vertex V now. So I can first of all set visited of V equal to true. And then I can have a for on all the adjacent vertices of vertex V. For that, I can have for int of u colon edge of V. Well, when I have a vector, I can use this syntax. I have a vector. This says that for each u on adjacent vertices of V. Now you can see that when I store the graph in a structured way in the computer, how easily I can just move on everything and find out that, okay, what are the adjacent vertices of this vertex. You see that I stored everything in a very structured way. For each vertex, I know that exactly what are the adjacent vertices of this vertex. So now I can easily use that. I have a for u on edge of V. Well, there's something that I want to say in here, but for now let's forget about that. What I want to do is that when I'm at vertex V, I want to now go and check vertex u. I want to traverse vertex u. So, okay, let's go from vertex V to vertex u and do whatever you want in there. Maybe you want to go visit some other vertices and so on. And after that, when you did that, then let's get back to vertex u again, to vertex V again. So our procedure is like this. We have V and we have this adjacent vertex u. We first go to u and we say that, okay, search there and do whatever you want. And then after that, come back to vertex V. And then the next time I check another adjacent vertex, for example, let's say vertex W, and then I go there and I say that, okay, go search and visit every vertex you want and then come back to vertex V again. So this is the procedure that I want to do. This is how I want to traverse my graph. Each time I go to an adjacent vertex and I want to visit new vertices. That's basically what I want to do. So I go to vertex u, and from vertex u I will go and visit every vertex that I can possibly visit. And then when I visited all of them and there's nothing more to search for, I should come back to vertex V. Because, okay, in here I have visited every vertices that were reachable for me from vertex u. When you come back, okay, you need to now search the rest of the graph. So you need to come back to vertex V so that next time you will check another adjacent vertex. So, but there's one condition that I should say before it. I mean, I do not always need to traverse U. There's something that I can say before that. Can you say what is that? I mean, I do not always need to traverse U. There are some cases that I do not need to traverse U and I do not need to do this work. That's not necessary. Can you say that? That you didn't. Exactly. If vis of U was false. Exactly. If already visited. Exactly. Well, the point is that if a vertex is already visited, then there's no need to go and visit it again, because it means that I was in the traverse function. The traverse function of that vertex is already called before at some point. So I say that if, in here, I say that if vis of u was false. Well, you know that I could also say that I could put an exclamation sign in here and forget about this part, and that will also work, but I want to write in the simplest way. So if vis of u was false, it means that this vertex is not visited before, so I do traverse. But if vis of u was true, if vis of u was true, then it means that the traverse function has already been called somewhere before. I mean, I have already visited vertex u before, and I've done everything from vertex u before. I mean, if the traverse function has been called, and from vertex u has done its job for searching. Vertex u has done its job for searching. It has visited all the other vertices and has reached every vertex that it could possibly reach. So there's nothing more to do in the subtree of vertex v. I'm done with it. So if it is already visited, there's no need to visit it once again. Do you agree? But only I do it if it is not visited yet. If it was not visited yet, I do traverse on vertex u. And that's basically all. I mean, let's just see that what does this code do. I mean, if I start from vertex v, let's consider this function. I start from vertex v. Whenever I see it, first I set it visited equal to true. And then I for on all its adjacent vertices. If they were not visited yet, I do traverse on u. Then what happens? If the graph is connected, I argue that everything will be visited, every vertex, and at the end I will just run in my main, it's just enough for me to, well, I have some code before it, but at the end it's just enough for me to just start traverse from vertex 1. Well, the point is that let's move these parts to somewhere else. I want to see that how this traverse function will work for me. So assume that my graph is like this. Again, consider I have a graph like this. So assume that this is my graph, for example. This is vertex 1, 2, 3, 4, 5, 6. The numbers I can be arbitrary, it doesn't matter. I chose an arbitrary vertex like vertex 1, and I started traversing from that vertex. Right? So what do I do actually? Well, first of all, I will, when I'm in here, I have a for on all my adjacent vertices. For example, first I see vertex 2. And when I make a vertex red, it means that it is visited. So first of all, I go to vertex 1. I make it visit. I make vis of 1 equal to true. Then I see vertex 2 as an adjacent vertex. And it is not visited. So I go and visit vertex 2. And from vertex 2, I will check its neighbors. For example, the first neighbor from vertex 1 that I see is vertex, for vertex 2 that I see is vertex 1 itself. In the adjacency list of vertex 2, I will find vertex 1 again. But 1 is already visited. There's no need for vertex 2 to call vertex 1, to call traverse for vertex 1. So I do nothing. In vertex 2, I do nothing. I just make visited of 2 equal to true, but I will not call anything else. At the end, as I said, I will come back to where I was. I will come back to vertex 1 once again, so that from vertex 1 I will search other branches as well, other places as well. So again on vertex 1, I go over the next adjacent vertex. I see vertex 3, I go to vertex 3. From vertex 3, I see its neighbors. I see it's the adjacent vertices of 3. There are 5 and 4. They can be in any order. For example, let's say that I first see 5. I come to 5 and I make 5 visited. So from 1 I came to 3, and then from 3 I came to 5. And again in 5 I see that my neighbors are vertex 1 and vertex 3. Both of them are already visited, so there's no need to 5 to call any of them. So I do just nothing in vertex 1. Let's show these back edges with blue so that it's clear. These edges that are blue, or let's use these edges with blue. These blue edges are the edges that will be called, I mean the other vertex is called. These red edges are when I just come back from when I was. I just come back. For example, with this blue edge, 3 will call 5, but 5 does not need to call anything. Everything is visited before, so I just come back to where I was at vertex 3. Now in vertex 3 I'm just keep searching on all the neighbors of vertex 3. I see vertex 4 and I see that it is not visited, so I'll go and visit it. So I'll go from vertex 3 to vertex 4. Then from vertex 4 I search under its neighbors. I see vertex 6 is not visited yet. I go and see vertex 6. I go and visit vertex 6. From vertex 6, my only neighbor is vertex 4 that is already visited. There's nothing that I can do for it. It is already visited. If it is still in process, it is in process and it's doing its work. If its process is done, its process is already done. So there's nothing that's there's no help if I call the transverse function on vertex 4 once again. So I will come back from vertex 6 to vertex 4, and then I come back from vertex 4 to vertex 3 because there are no neighbors, and then I come back from vertex 3 to vertex 1. Then I'm back at vertex 1 and I check another neighbor that I have which is vertex 5, but I see that it is already visited, so there's nothing needed to do there. So I do not call it, and I'm done with my traverse after that. I just return from traverse of vertex 1, and this way I see that visited of all the vertices is true. I can also keep a counter. I can also keep a number named counter that it counts that how many visited I saw. Whenever I visited a new vertex, I can say counter plus plus. At the end, I can check that. I can say that if my counter was equal to n, it means that I have visited all the vertices. So I can see out connected, all the visited are all the vertices are visited. Otherwise, let's just use a simple if and else. Otherwise, I can just see out it is not connected, it is disconnected, for example. So basically what I do is to start DFS from a vertex, from an arbitrary vertex. It can be, for example, vertex 1. It would also work if you would use vertex 2 or vertex n. Any vertex would work. So I do a DFS from that, I do a traverse from that vertex, and I try to find out if all the vertices will be visited. And if all the vertices were visited, then the graph is connected, otherwise it is not connected. Is it clear? If it is clear, please again use this emoji, or yes, sure. Yes, sure. Please in the Kevin, in the group, reply to your message. I have missed it. Reply to your message. I try to answer it. So let me also send you the address of our Telegram channel. As you can see in here, this is our Telegram channel. If you had any doubts or issues, you can always post them in Telegram channel. If I see them, I'll answer them. Or there are so many other people there as well. You can also discuss with each other, and there are other people who answer your questions and doubts. So this is the link of the channel. I also put the link of the group in the channel. You're more than welcome to join our Telegram channel. So do you have any questions so far? Everything clear? So this is how we can traverse our graph and find out if it is connected. Nice. I will answer this later on. This is good if you ask this question also in Telegram. We will talk about all this. If bool array is not initialized, yes, if you define a Boolean array globally, it is initially set to be false. Like if you define any integer globally, it is initially set to be 0. If you define them globally, yes, that's gonna work like that. About mod, yes, in future I will talk about mod as well. Not right now, but I will. Yes, sure, I will cover. That's exactly the goal. I will cover all the important graph algorithms, all of them, all the graph algorithms in the future streams. This is just the first stream, but we're gonna cover everything in the future as well. We're gonna go over all of them. So as you might see, so we have this traverse algorithm that helps us to find all the vertices and visit all the vertices, and we checked if all the vertices are visited or not. Well, I mistakenly once used the word DFS instead of this traverse, but it had a reason. This algorithm, this traverse that we used in here, this has a name. This is called as depth first search, or in short, DFS. This is DFS. What we did in here was DFS. That is exactly this logic that I explained. We start from a vertex and we go over all its neighbors. If they are visited already, we just skip them. If they are not visited, we call them. And we call the function with those variables. This is called, what we did in here, this traverse function is called depth first search, or DFS. So you might have heard the name of DFS before. This is what DFS is doing. It just has a for on all the neighbors, and if it is possible to go there, and if they are not already visited before, we will go to that vertex. This is called DFS. Is it clear? So basically we have not talked, without mentioning the name of DFS, we have talked about DFS. This was the first thing, that the first algorithm that you need to be familiar with in graphs. This is how we have used DFS. We have used DFS in order to find out if the graph is connected. Okay, so now let's try to solve some problem from Codeforces now. Let's start seeing that what we can expect when we're solving problems on graphs. When we want to solve a problem on graph, what we can expect on Codeforces. So this is the first problem that we're going to discuss. Mr. Kitauta's colorful graph. I sent you the link in the chats. So it is just saying that Mr. Kitauta has just bought an undirected graph. Now you are familiar with these words. You know that what an undirected graph means. And when it doesn't mention anything about being weighted or unweighted, it means that it is unweighted. Okay, in here it doesn't mention anything whether if it is weighted or unweighted, so it is unweighted. but an unweighted, undirected graph consisting of n vertices and m edges, the vertices of the graph are numbered from 1 to n. Each edge, namely I, has a color Ci, connecting vertices AI and BI. Mr. Kitayuta wants to process the following Q queries. In the ith query, he gives you two integers ui, u sub I, and v sub I. Find the number of colors that satisfy the following condition. The edge of that color connect vertex ui and vertex vi directly or indirectly. So, what it is saying? Basically, what it's saying is this. You have a graph. Well, it is not weighted, and I'll tell you why I'm saying that it is not weighted. Because I'm gonna split the graph by the colors. But let me first tell you that just this. We have a graph that each edge has some color in it. For example, the color of this edge is C. So maybe you can look at it like a weight on the edge, but we will talk about why this is not going to be important and it doesn't need to be considered as a weight. Each of the edges have some color, and each time we have Q queries, and we know that the number of vertices is at most 100. As you see in here, we can find the limits here. As I said before, in our computer, we need to have some limits on the number of vertices and the number of edges that we have. N is up to 100 and M is up to 100. So the number of vertices and the number of edges are up to 100. And Q is also up to 100. So you also have a Q, and you have Q queries. Each query you are given two values, UI and VI, which are two vertices in your graph. And what you need to say is that for how many colors. We know that each edge has a color, so each color has a graph for itself. If we just gather all the edges with that specific color, we have a graph with that color. So you have UI and VI, and you want to find out for how many colors UI and VI are connected only using vertices with that color. So for how many colors like C, UI and VI can be connected with each other only using edges of color C. And we know that the number of colors are also up to M. So colors are from 1 to M, and M is up to 100. So each edge has a color. It's like each edge has a number for it, and it's the color of that edge. And each time you are given two values, UI and VI, you want to find out that for how many colors UI and VI are connected with that color, with the edges of that color. Is it clear? Yes, I will cover DSQ in the future graph streams. Yeah. As I said, all the topics will be covered. So if it is clear, please use this emoji again. I think now we have some delay. Yes, that's a good idea. If the statement is clear, we're gonna not talk about how to solve this problem. Nice. So, well, basically the question is this. It's like, well, we know that the colors of the edges are from 1 to M. So we can say that it's like we have M graphs. In the first graph, I only consider the edges with color 1. In the second one, I only consider the edges with color 2. And in the last one, I only consider the edges with color M. And now, my question is that in how many of these graphs UI and VI are connected? Well, what I can do is very similar to what I did in here. In here, I was trying to find out if all the vertices are reachable from vertex 1. This time, what I need to do is to find out that if from vertex UI, I can reach vertex VI in any of these graphs. And this is what I did in here as well. I did not talk about time complexity of what we do in here. We don't still have complete idea about why it works, but I didn't want to get into that for now. In the next session, we will talk about what is the time complexity of this function, with this, what we did, this algorithm. But for now, we know that we only are considering it for small values. In here also, n and m are up to 100, so we do not need to worry about our code being so slow. So for now, let's just say that for each of these graphs, we want to find out if from UI, VI is reachable or not. What we can do is to just have a for on all these graphs. So we have a for of size m, at most 100. And we can store all the edges of each color. So now, for our adjacency vector, we can keep an n by m list. That n is the maximum number of the vertices, m is the maximum number of colors. Both of them in this question are at most 100. As I said, we also add some small value to our numbers as well. So we have adjacency list for each color. So when we have an edge, when we seen U and V and C, in adjacency list of U and C, so all the adjacent vertices of U with this specific color C, we push back V. So this is all the vertices adjacent to U in graph number C. As I said, it's like we have m different graphs, and each graph is undirected and unweighted. And in that graph number I, we only consider edges with color number I. So what I do is that I say that edge of U and C dot pushback V and edge of V and C dot pushback U. So we have these graphs in a we have stored this graph in a very structured way now. So now what we want to do is to just start traversing this graph. We have a for each query. Now we're talking about our queries. We have a for on the color of the graph. We have int of C equal to 1, C less than or equal to M, C++. We just say that let's start traversing. First of all, we make visited for all the vertices equal to false, for int I equal to 1, and as I said, for now we're using 1 based indexing, so our vertices are numbered from 1 to n. Initially we set visited of each vertex to false. This time, because we run traverse so many times, each time we need to make our visited equal to false once again, because last time we have used it and we have changed some of them. Now for our new DFS, for new traverse, we need to make them equal to all, initialize them all again. So we need to make all of them false again. And now let's traverse, or as I said, we can this time use the name of DFS because we said that this is named DFS. We can do DFS of vertex U with color C, and we will implement inside of DFS, and we will see that how we can do our work inside DFS. But afterwards we just need to find out if vis of V was true. U and V are the vertices that we are given in our query. If visited of V was true, we can just say that we have a counter, and we can say that counter plus plus. We have an int of counter that is initialized to 0 at the beginning. And at the end, it's just enough to see out counter and endl. This way we can find out for how many of these graphs V is reachable from U. And how does our DFS work? This DFS is defined above everything else. But I write it here on the tablets. We have void of DFS. We have two vertices. We have two arguments for it. We have a vertex like vertex V, and we have a color like color C. Color C shows that which color we care about, vertices of which color we're talking about, and vertex V is the vertex that we are already in it. And then inside it, first I say vis of V is equal to true. It's very similar to the function that we implemented so far. It's exactly the same. The only difference is this. We have a for int of U on edge of V and C. So we only care about edges and vertices of V that have color C. Because right now we're only talking about the edges with color C. And then I say that if not of visited of U was not true, and I can also show it like this. This means that if vis of U was false, if you put an exclamation sign before a variable, it means that if that value is either 0 or false, so it means that its value is either 0 or false. So if it was false, just do the DFS of U and C. And only by doing this, we can visit all the vertices starting from vertex U. And then if vertex V was at the end, not this V. This V is a variable inside the scope of this function. But for this U and V that we had in here, if vis of U was true, then we say counter plus plus, and at the end we see out counter and then. And this way we can find out if only with color number C we can visit all the vertices or not. We can visit vertex V or not if we start from vertex C. Is it clear? If any part was not clear, let me know. It is completely okay. I know that I explained it in a very fast way because I wanted to be able to solve another problem in the live stream as well. Before the stream ends, I went too fast. So maybe you need to watch this part of video once again. This will be recorded and it's available on the channel. And maybe you are already watching its recorded version. So maybe you need to watch it again. And if it was not clear, let me know to explain it again. Yes, I agree. It was a bit fast. So if it was clear for you, please use this emoji. If it wasn't clear or write in the chat. If it wasn't clear for you, let me know to explain it again. I want to see that for how many people it was clear, for how many people it was not, to know that, how much time to spend to explain it again. Okay, so I just explained it very briefly once again, if for most of you it was clear. Just for 2 or 3 minutes. I explained it very briefly once again, and as I said, you can also watch the recorded version as well to make sure that you're okay with it. So in this problem, if the statement was clear, we wanted to find out each edge had a number on it, which was the color of that edge. So we have a graph, each edge has a number, which is the color of that specific edge. And now we want to find out, we have Q queries. In each query, we are given two numbers, UI and VI, and we want to find out that how many colors exist if I only consider the edges with that specific color, UI and VI will be connected. So this is query number I. This is query number I. That we have two numbers, UI and VI, and we want to find out for how many colors it is possible to go from UI to VI. Or in other words, I want to find out for how many C's VI is reachable from UI, from U sub I. I want to find that out. Well, what I said was that I do not need to do any additional thing compared to what I was doing before. I can use that DFS method once again. I can use that DFS method once again and just find out if VI is reachable from this UI. This time, instead of seeing that if all the vertices are reachable from vertex 1, the only thing I care about is that if I only consider edges with color C, VI is reachable from UI or it's not reachable from UI. If I only use color number C. And in each query, well, first of all, I do not need to store these sub-i's. I can just, in each query, I can just consider two values, U and V, define two values, U and V, and I can just see in U and V. I do not need to store these sub-i's because each query can be solved independently. And then I can have a for on all the colors, for int of C equal to 0, C less than N, C plus plus, C less than M, sorry, C from 1, C less than or equal to M, and C plus plus. I can start the traversing from vertex U and with color C and find out if vertex V is visited or not. Before that, I should make visited of all the vertices to false. I just use pseudocode in here. I should make visited of all the vertices equal to false for all I from 1 to N. And then after that, I need to check if V is visited or vis of V is true. So I'm just considering edges of color C. Where do I only consider edges of color C? Where in my DFS I pass this C and my for is gonna be only on edge of V and C. I only consider all the edges that are from this color. If you remember that how I was storing the edges, whenever I get U and V and C, I say that in edge of U and C, push back V, in edge of V and C, push back U. So edge of V and C means all the adjacent vertices of vertex V with color C. So I only have a for on those color, on that specific color, and if a vertex was not visited, I will call DFS on that vertex. This way, I can find out all the vertices that are reachable from vertex U if I only consider edges of color C. And if V was reachable from U, then I can say that this color works, and with this color U and V are connected. Otherwise, it is not. This color must not be considered. In this case, I say counter plus plus. There, I found one more color that works for me. And then at the end, I just need to see out counter. If it is clear for you, please again use this emoji. Or write that in the chat. And thank you. Nice. Nice. If needed, you can always watch the video once again as well. I'm sorry that if we just need to sometimes skip because we want to cover the other topics as well. But it's always possible if at any point you think that it is needed to watch it again. Explain about the color. But color is very simple. It's just saying that we want to find the number of colors that only considering edges of that color we can get from U to V. So it's like each color forms a different graph. We have a graph only with vertices of color 1. We have a graph only with vertices of color 2. We have a graph only with vertices of color 3, and so on. So this is the point of the colors that we have. We want to see that in how many of these M graphs U and V are going to be connected. Okay, so we want to see that in how many of these graphs U and V are going to be connected. What we can do in here is to just store these graphs of different colors into different vectors. So for each v, edge of v and c means that how many, which adjacent vertices do we have for vertex v with this specific color. And when we run in DFS, we run only DFS on edges with that specific color. And this way we will solve this problem. Is it clear? Nice. If you still have any questions, you might ask them. And maybe it's good if I also show the code. I can skip this one, but it is better if I also show you my code for this part. This code is not a very good code. It's not best practice. As you can see, I've submitted this code in year 2015. So it's only 1 year, around 1 year, or maybe less than that when I started, because I started in very late 2014. I remember that it was after the World Cup of the year 2014. So it is maybe less than a year before I from when I started competitive programming. So the code is not in the best shape, but I want to show you that how I implemented it back then. I think it's going to be helpful. So I see an A, B, C, and you might ask what these minus ones are. Can you say that what these minus ones are? Thank you a lot. Yes, definitely. I will cover everything. This is only the first topic stream, so don't worry about it. We'll get to a lot more challenge. We're covering the basics for now, mostly. But I wanted to cover some challenging problems even in the first live stream as well. Maybe we won't have time for that, unfortunately. But in the second topic stream, we're gonna solve a lot more challenging problems. Yes, exactly. This is for zero-based indexing because A, you know, the point is A is from 1 to n, right? But in our codes, it's always better if we make everything zero-based indexing. We're gonna talk about why it is way better and way cleaner. You will see that, for example, when we talk about prefix sums, we see that how cleaner it is when we use zero-based indexing instead of one-based indexing. And even the things that are defined by C++ themselves, like vectors, like strings, they are also zero-based indexed. When we talked about vector, we saw that the first index of the vector is v of 0, the second one is v1, the third one is v2. So it's better if we can make the indices from 0 to n minus 1. Less than, strictly less than n. So that's why we say minus 1 in here, so that 1 maps to 0, 2 maps to 1, 3 maps to 2. And for C that's the same. 1 maps to 0, 2 maps to 1, and so on. So that's why I used minus 1. It is not very good because it was way cleaner if I would just say once A minus minus, B minus minus, C minus minus. That's way cleaner because this way maybe in one place you forget, or maybe you want to make some change. And this way you have to make the changes in all these places, which is not good. So it was cleaner if I would first say that A minus minus, B minus minus, C minus minus, and then we're done. Then we do not do any minus 1 plus 1 anymore. And then I use for Q minus minus. Instead of this, I could also say while, and then in brackets Q minus minus. I see in UV, and here you see U minus minus, V minus minus, I make them zero-based. And then I have for, I have defined for. I used to define for back then, but this is not a good thing. Don't do that. Just write for. I do not do this anymore. And first, I set visited of everything equal to true. And then I do the DFS that I was talking about. I do DFS of U and I. And then if V was visited, I say CNT plus plus. This is my counter. And then at the end, I see out CNT. So what does this DFS do? First, it gets two variables, DFS of where is short for vertex, and col. which is the color, it stands for our color. Visited of where is equal to 1 or true. When we are talking about booleans, we can both use 0 and 1 and false and true. 0 means false, 1 means true. So if I write 1 in here, it means that viz of v is true or it's 1. 0 and 1 are false and true. Then I have a for on all the adjacent vertices, and I say that if edge of where of col and I, but in here I have a for on all of them, and my new vertex is gonna be, this is the vector that I have, vector of adjacent vertices to where. If the number I of this vector, if the element at position I in this vector was not visited, I say DFS of, I call the DFS of this vertex and this color. At the end, it's just enough to find out if visited of v was true. Is it clear? Thanks a lot. Thanks a lot, guys. Is it clear how was this code? Yes, you can write it in Telegram. I cannot write now with the Telegram after the live stream. After the live stream, I'm gonna have a meeting in the university, but I will check Telegram. Thanks a lot. Thanks a lot. And okay, so I'm gonna also give you some intuition about how the next topic stream on Graph is gonna be. And before that, guys, if you want to support my work, you don't need to do this, but if you do, that definitely helps a lot. You can like the video, subscribe to the channel, and especially if you can tell about your feedbacks in the comments for this video, that's gonna also help a lot. I mean, that's okay if anything is your comments. I mean, give me your truthful comments. You don't need to say good things or bad things. If you see, I think it's either very nice if you say your objections to the live streams, because in the next live streams I'm gonna try to make them better, and this way we can improve. So feel free to tell me in the comments of YouTube or in Telegram or anywhere. Tell me about the issues that you find in the live stream and how we can make it better for you. And also in the YouTube, if you can put comments, I think that's gonna be very helpful. If you want, you can do that. And also about the next session, there's something that I wanted to also talk about and solve the problem with that as well. There's some type of graphs that we call bipartites. I just give you a summary, but I'm gonna explain it in more detail in the next session, and we're gonna solve a harder problem on CF using this concept. Bipartites, a graph is bipartite if you can split it into two parts, and you can say that all the edges are from one of these parts to the other parts. So if you are able to split the vertices into two parts such that all the vertices are from one part to the other parts, there is not going to be any edges, all the edges are from one part to the other part. It is not possible to have an edge from one part to itself. That never happens. These graphs are called bipartite. Some graphs are bipartite, for example, like this graph that I'm writing here is obviously bipartite, but some graphs are not bipartite. For example, if you have a triangle, it's never possible to split the vertices into two parts such that all the edges are gonna be between two parts. Because whatever you do, when you have three vertices, whatever you do, one side is gonna have at least two vertices, and those two vertices have an edge to each other, which is not good. We said that we want all the edges to be between these two parts. Okay, so some graphs are bipartite and some graphs are not bipartite. And this is also a very interesting thing, and that's gonna help in a lot of problems. And we're gonna use it in a problem on Codeforces in the next session. And we're gonna cover more complicated problems on graphs as well. I hope that you understood everything that is needed. Make sure to, if needed, watch some parts again so that you get a complete understanding of whatever we mentioned, because in the next sessions where we want to cover more advanced topics, it's so important for you to first be familiar completely with these basic topics that we covered at the beginning. So make sure that you're completely familiar with them. Make sure to accept that problem that we were talking about today in Codeforces. That's gonna also help a lot. I don't know why I look there, sorry. Make sure to accept this problem that we were talking about, and so that you will be ready for the next topic streams. Okay. Is it anything that you wanted to say? And again, as I said, you can join our Discord server or Telegram channel if you had, if you wanted to have any further discussions. So this is the link of the Telegram channel, whichever that suits you the best. And this is the link of the Discord server, whichever that works the best. You can talk about, have further discussion there. Thank you very much for joining. It was so nice to have you again in this topic stream. Hope to see you next week as well. Next week still we're gonna be in graphs, and also if you want, before this we had three sessions on DP. That is gonna help a lot as well, and maybe we do some parts of DP in here as well, because in future we see that some graph problems can be solved using DP as well. So I mean, you use both DP and you're gonna use both DP and graphs to solve them. Especially there are a lot of DP problems on trees. So make sure to watch them as well. I send you the playlist. You can find all our topic streams in this playlist. And if you had any questions, I will try to answer them in Telegram or Discord. Especially, yes, about backtracking, I will talk about that as well. I have a video for recursion. Maybe for your question, I should send you the link of that video. You can watch this video about recursion, which is exactly that backtracking that you're talking about. You can watch this video, and I hope that one will help. Alright guys, nice. Again, thank you a lot. Hope to see you once again in the next topic stream on graph. See you guys next time. Bye bye.